purpose of this section is to answer the question we raised the first section, that actually any analytic function has derivatives of any order. Okay, so we are going to prove this result. Okay, all right. So we will have this version that we are simply connected domain. Domain in the complex plane. So D is simply connected domain. F is an analytic function on E. Alright, so let Z0 is in D, okay, and we let gamma be a simple closed path in the domain. Okay, that moves counterclockwise. Okay, and enclose 0. All right, so this implies that the index, all right, the index of Z0 with respect to the simple closed path gamma is equal to 1, because that move counterclockwise, okay, and enclose it, right? And because it is simple, so that the index is equal. Right, then we have derivative, okay, of the analytic function f at the point 0, and this derivative can be expressed by a complex integral. Okay, so very similar to the Cauchy integral formula, but this time the denominator is the square of z minus z0. Okay, 0. And also we can have the second derivative. So we have the 2 factorial pi I. Again, we have express the second derivative by using the complex integral. In general, okay, we have nth derivative of f at the point z0, right? And it is n factorial divided by 2 pi I. And then the complex integral along the simple closed path gamma, and here the power of the denominator is n plus 1. Okay, the proof is a little bit lengthy, but it is not difficult because we already developed Cauchy's integral formula already. So actually, the proof of this theorem is based on the Cauchy's integral formula on simple connected domain for simple concept. Okay. So the point is that remember, so actually this is true for n from 0, 1 to etc. If n is 0, actually this is just the function itself, right? So when n is 0, it is the Cauchy integral formula itself, because the index of z0 with respect to the simple cross path gamma is equal to 1. Remember, if n is 0, we have to put the index in, right? But because the index is 1, so we can just write the Cauchy integral formula like this. Okay, so this is the direct extension of the Cauchy's integral formula. And so, okay, so now we can state a consequence of this theorem. So if omega is an open set in the complex plane, and if f is holomorphic, right? So if f is holomorphic on the open state, then the derivative of f is also holomorphic. So this is the consequences. But so the proof actually is quite simple. So we let z0 in the open set, right? This is very general. This omega is just an open set. Okay, it's an open set. Okay, so we have this is omega, and we have z0 here. Okay, and because omega is open, so that we can have an open disk. Okay, so we have an open disk. So this is D, this is 0. Since omega is open, right? There exists an open disk. Then D, Z0 R, okay, with center Z0 and the radius greater than 0 contained in omega. Okay? Alright, so that's E Z0 or the open disk is simply connected. So it's simply connected domain in a complex plane, and F is analytic on B Z0R. Okay, so F is analytic. Now we need to apply a theorem. We need a simple cross path, all right, in cross this zero, right? And this simple cross path should be in the simply connected domain of the disk. So, so we arbitrarily select another disk, another, all right. So we will actually construct a circle. Okay, so we construct a circle here. So we so the positively oriented circle, with the center Z0 and the radius R divided by 2. Okay, so this is gamma. Okay, it's a simple closed path in the simply connected domain D0 on. Okay, which moves counter clockwise. Okay, and in cross is 0. Okay, as required in this theorem. This is the theorem. All right. So now, by theorem 14.1, okay, the derivative of f prime exists. Okay, at Z0. E f prime. Okay, it's equal to okay. So we have that. Okay, so it's right, so the derivative of f prime exists, okay, and we know how to compute it, right? So since Z0 is an arbitrary point in omega, f prime is so f prime is holomorphic, means that f prime itself is an analytic function on the open set. So you can see, even though the theorem is kind of restrictive, means that the domain is a simply connected domain, and that the path is a simple cross path. Right? But the result is already powerful, right, to prove such a general result. Any questions? Okay. Now, sometimes we like to estimate the nth derivative of an analytic function. Okay, so we will develop coefficient inequality. All right. So suppose we know that f is holomorphic in a disk. Right. So f is holomorphic in a disk with center A and radius big R. Okay. So we know that this disk is simply connected domain, right? And f is an analytic function. And quite often we know that, right? We know that the function, the analytic function is bounded. Okay, for all C in this disk, right? Then actually we can estimate the S derivative, right? At the center, right? We can estimate that. And this estimate is actually n squared, n factorial times big M, the upper bound here, but divided by r to the n squared, and for any n, etc. Okay, so this is the quite often it is a good estimate for application. Okay, and actually the proof is that by applying theorem 4.1, because we have an expression of the nth derivatives of the analytic function at point A. Okay, we have that. We express that by using a line integral. So actually this is quite simple. So we select with simple closed terms, which is the positively oriented circle, okay, with center A and the radius little r. Mix that up. Okay, so the gamma actually is equal to A, the center, little r, gamma little r, E I 2 pi t. T is from 0 to 1. Okay, so the simple closed path we select to be the positively oriented circle. Okay, because the disk, we know the disk here, and we have okay, so this is B, then R here, right? So this is the simply connected domain. Okay, and we select okay. And the R, the radial R is chosen to be less than big R here, right? Less than big R. So that the gamma star is in the disk. okay, in disk, and enclose the point A, right? And so so we have, okay, this is equal to n factorial 2 pi I. Here, right? This is from theorem 14.4.1. Right, so we have that. Okay, and so of course this is less than equal to n factorial 2 pi. Okay, and gamma fz e minus a n plus 1 dz. Okay. If you don't like this expression, actually this is just the differential arc length. But if you don't like that, that's fine. We can do it in this way. You are right, and this is f gamma t. Right, and so this is gamma t minus a gamma t dt. Okay, so we can just apply the line integral to it. So this is 1, and then we have 2 pi. Okay, now we move the absolute sign into the integral. Then you should have put an inequality. Okay, as we know from okay, and now because the gamma t minus a is here, right? So we know this is r. Okay, e I 2 pi t. That's the value. Gamma prime t. Okay. Now. Now, the denominator, because the exponential e to the I 2 pi t is equal to 1, right? So we know this is equal to r. Okay. But the numerator is less than or equal to m. Why? Because the range of the simple cross path gamma star is in the disk, right? And we know. In this disk, the function value is upper bounded. The absolute value, the f value of the function value is upper bounded by m. So we have here, okay, and so now we have n factorial big M 2 pi. Oh, n plus 1. Okay, and r n plus 1. Right, and 1 dt. Okay, and actually this is the arc length, right, of the circle, right? And so this is the arc length. So what is that? It's 2 pi r, right? 2 pi r. And so the result is n factorial m and r n. Okay? Okay, so the absolute value of this nth derivative of the function f at point A is upper bounded by this number. Okay? For all, and this is true, right? For all r less than r. Okay. So now, by dating, I'm going to pick up. So we have Okay, so finally we have this result. Okay. All right, now, a complex function, okay, which is analytic, all right, which is analytical on the whole complex plane, okay, is called, okay, and it's called an anti-function. For example, the exponential function is an entire function. Okay, so the exponential function is the entire function. Okay, so we now state Liouville's theorem. Okay. Every bounded anti-function is constant. Okay, so if we have an anti-function, all right, and if we know that the anti-function is bounded, it means that at every point in the complex plane, the value is upper bounded, the x value is upper bounded by some number n. If this is true, then the anti-function should be a constant function. Okay, so that means that a non-constant anti-function should be unbounded, like exponential function. The exponential function should be unbounded because it is clear it is not a constant function. Okay, so and so this is called Liouville's theorem. Right, so the proof actually is quite simple. Once we have the Cauchy's inequality, like this one. Okay, so now since f is entire, okay, since f is entire, f is analytic. The disk Z0 for any Z0 and any greater than 0, right? F is entire. So at every point in the complex plane, F is analytical in that disk. Okay. Right now, since F is bounded, right? There exists an m greater than 0 such that f of z is less than or equal to m for all z in the complex plane. Now, by Cauchy inequality, okay, we have f from z0 is less than equal to m divided by r. Okay, this is by Cauchy's inequality for n equal to 1. So the derivative, right? The derivative is less than equal to m. And this is true, right? This is true for all r greater than 0. So now, by letting r goes to infinity, so we have f from z0 is 0 for all z0 in the complex plane. So immediately we have this result. Okay? So the derivative is 0. Okay? So of course, so that f of z is constant. Okay? So it's constant on C. That's quite simple. You see that? So Differential theorem looks very simple, but it has a lot of applications. Okay, because that in many times you conjecture some function you are studying is a constant function, and the way you can prove that is by applying the Differential theorem. Okay, you prove that it's an anti-function, and second, you prove that it's bounded, and then by Differential theorem it's constant. Okay, now the last theorem in this section is a kind of converse of the Cauchy integral theorem. Okay, a kind of converse. Because remember, the Cauchy's integral theorem says that if a function f is analytical, okay, in some open set, like especially in the global Cauchy's theorem, then the line integral of this function around cycle basically is equal to 0. Okay, this is the spirit of Cauchy's integral theorem. So the premise is that you have an analytic function. Okay, so now we will give a version of the converse of the Cauchy's integral theorem. It's called Morera theorem. Right, Morera's theorem. All right, now, so f is a continuous complex function. Okay, on an open set omega. Okay, so omega is an open set and f is continuous. Okay, on open set, such that we have a complex integral, right, along the boundary of a triangle. Okay, so this is for every closed triangle. Okay, here we come, contained in omega. Right, so then f is holomorphic. Okay? Then f is holomorphic. It's quite useful. Why? Well, you have a lot of good things if you know f is analytical. If f is analytical, then the f prime is analytical. F dot prime is analytical, right? Everything. So analytic function has derivative of any order. Okay, and for analytic function, you have Cauchy's integral theorem, you have Cauchy's integral formula, a lot of good things you have, right? So it seems like you should know some complex function is analytic. But how? Do you have a tool, right, to justify, right? Once you are given a complex function, can you justify it is analytic? Right? So here, the Morera theorem gives you a positive answer. Okay? So of course, you know, we prove that any analytic function is continuous, right? So continuity is necessary. Right? It's necessary. So you should have a continuous complex function. Because without continuity, don't say anything about the differentiability. Okay? So first of all, you should have a complex function which is continuous on an open set. And then you justify that the line integral of this continuous function over the boundary of any cross triangle in omega. This should be true because the triangle here be any triangle, anyone, right? In this omega. And along the boundary, you get this result. Then if this is true, then f should be analytical. Okay? It guarantees you the analyticity of the function. Okay? So this is quite useful in theory as well as in application. Because you know at first hand that the function, the complex function you studied is analytic. Okay, and this gives you one way to do that. Okay, and very powerful because the triangle, you have only 3 edges, and each edge is just one segment, right? One segment. So it's quite easy to deal with the line integral, to evaluate that, to justify. Okay, and I think I leave the proof for you. Okay, so now we go to chapter 15 to elaborate more properties of analytic function. And I believe you are well prepared. I assume you already read the first section. Okay. All right. So let me just kind of state some important theorem. Okay, mentioned here. In all series and the Taylor series. All right. So the first section is about convergence. Okay. Convergence test of infinite series. Okay, and so we are talking about infinite series with complex functions. Okay, so let me just write down some of the good results. All right. Okay, so let's see. A list of useful tests of convergence. Okay, of infinite series of complex numbers. Right? So this is the basic. Before we are able to study the power series with complex coefficients. Okay, so we let's just list some of them. From 1 to O, okay. The root test. And I believe some of you is familiar with this test, at least in real number, or sequence of real number in calculus. So now, suppose we are given an infinite series. Okay, from 1 to infinity, Cn of complex numbers. So Cn are complex numbers, okay? So this is an infinite series of complex numbers. We let alpha to be the lim suit of the nth root of the nth coefficient, the nth term, right? So you take the absolute value of the nth term, and then take the nth root, right? And then take the lim suit as n goes to infinity. Okay? And I believe you already know what is the lim suit, right? Okay. This is the reason why I asked you to study this section. Okay, then, first of all, if alpha, by the way, I have to say again, for any sequence like this one, right? Any sequence, you may have a limit or may not have any limit, right? Limit may not exist, but lim suit always exists. Okay, this is the reason why this is always exists and alpha always there for you, okay, to do the test. Okay, you need something, right? Testable. So this is a testable test. Because if alpha does not exist, then you can come to any test. Okay, so we use lim suit. Now, if alpha is less than 1, then this infinite series converges absolutely. Okay? The second thing is that if alpha greater than 1, then the infinite series diverge. Okay? So alpha, so 1 is an important threshold. Okay? But if alpha is equal to 1, then the test is failed. Okay? So the test of convergence of the infinite series, okay, is inconclusive. So you don't know. Okay, so you should elaborate it. Okay, if alpha equal to 1. So if alpha equal to 1, the infinite series may be converged, or may not converge. Depends on what is this infinite series. Okay, all right. But at least if alpha is greater than 1 or alpha is less than 1, you have your conclusion definitely. Okay, so this is the power of root test. And so, remark, we know if the limit All right, if this is sequence, all right, it's a sequence, right? So if the sequence has limit, here I use limit, right? So if the limit exists, then we know, then alpha, the limit is equal to the limit, of course. Right? All right. So if you know the limit of this sequence, then the lim sub, of course, is equal to the limit, of course. So if you know, and then you can use the test, the Lu test, to make a conclusion about this infinite series. But in many situations, the limit does not exist. Okay, but you still can find a lim sub for that. For example, I believe if you study the material, if Cn, okay, so if Cn is equal to I to the nth power. Suppose this is the 1, right? So of course the observation to the 1, but so for example, 1 Cn here. So now Cn is equal to 1, okay, and is equal to 1. So you have limit. Okay, you have limit, and this is equal to 1. Okay, this is equal to 1. All right, so that, and this is alpha, and this is equal to alpha. So alpha equal to 1, and now the test is that it's inconclusive. And not do anything, even though you know that is the case. All right. The second thing is that if you have so if you have like Cn is equal to half and the In. Okay, so you have Cn like this one, and n equal to 1 to etc. That. And in this case, that Cn is equal to 1 over 2 to the nth power, and so Cn to n is equal to 1/2, and it's 1/2. So the limit is 1/2 is equal to alpha, which is less than 1. So you know that if the term Cn is like this one, then the theories converge. Okay. All right, so you have a lot of things like that. Okay. And the other useful test is the ratio test. Okay, so so again, an infinite series of complex numbers. Okay. First of all, it converges, right? Absolutely. If the lim sub goes to infinity of the ratio. Okay, so the ratio is that the terms, the n plus 1 term divided by the nth term. Okay, nth term. Oh, okay, and we require something because we will put the terms in the denominator. So here we need to consider different theories of non-zero complex numbers. So Cn are non-zero complex numbers. Okay, and so we are not be embarrassed. Okay, to encounter the case that some denominator is 0, so it not happen. And so if this one is this one, right? Again, so if the lim sub, because this lim sub always exists. Okay, and the lim sub is less than 1, then this series, okay, this complex, the series, infinite series of non-zero complex numbers, is converge absolutely. But it diverge. All right, if there exists an integer, so there is this n greater than 0, such that, okay, the ratio, okay, so the absolute value of ratio greater than or equal to 1 for all n within the range. Okay. So you have two cases to consider. First of all, you compute the lim sub of the absolute value of the ratio, right? This number always exists. Okay, and if this is less than 1, then you know the series converges absolutely. The other way, if you want to prove it's diverge, then you have to show that if n is sufficient big, then the ratio, the absolute value of the ratio is greater than or equal to 1. You need to show that. Okay. And if you don't know 1 or 2, then it is inconclusive, right, to use the ratio test. Okay. Because sometimes it is a little bit harder to find the lim sub, this lim sub. Okay. So the ratio test gives you a good test with that. So so this is the two basic tests that we can have. Okay, one is the Lu test, the other is the ratio test. And we would basically, in theory, we use Lu test quite often, right? Then more often than the ratio test. Okay. Okay. So it's kind of an introduction to this chapter, and I hope you get through the first section, and then we will develop the rest of chapter 15. Okay. Thursday. So do you have any questions? Okay. So if no, I will see you on Thursday.